Hi everyone. I wanted to go over two examples of solving problems involving rotation today. The first one, we're going to see how to convert between linear values like linear acceleration and linear velocity to angular values like angular acceleration and angular velocity. In the second part, we're going to see how to convert between linear kinetic energy and angular kinetic energy. And we're going to connect that to our relationship between linear and angular velocity. So for the first problem, I want to look at Young and Freeman, problem 922. In this one, you're trying to design a cylindrical axle to lift 800 Newton buckets of cement from some rooftop. And what the question is asking it for at first is what should the diameter of the axle be in order to raise the buckets at a steady rate of 2 centimeters per second when it is turning at 7.5 RPM. Okay? So what you should do in this case is draw a diagram. Okay? We have some cylindrical axle with some radius r. It's asking note for the diameter, so this will be 2r. And we're lifting some buckets. Here's my crude drawing of a bucket. Up this axle with a velocity of 2 centimeters per second. In this case, let's say in z, going up. And we know that this is turning at some rate of a period of 1 over 7.5 minutes. Okay? So the first thing we need to do is we need to convert velocity into angular velocity, right? And we know that omega r equals v. And what I want you to think about this problem is this is known, and this we can calculate. Okay? So the velocity here is 2, or the magnitude of the velocity is 2 centimeters per second. I apologize for the sirens in the background. And the angular velocity, omega, right, we're going to need to get it into the right units, and we're going to need to calculate it. So we know that the angular velocity in some units is 7.5 RPM. So this will be 7.5 rotations per minute times 2 pi radians per rotation times 1 over 60 minutes per second. Okay? So rotations cancel, minutes cancel, and this gives us units of rads per second. And this is equal to, once you do all the math, 0.78 rad per second. Okay? So that's omega. So if the magnitude of V is equal to omega r, then r is equal to V over omega, which is equal to 2 centimeters per second over 0.78 rad per second, which is equal to 2.56 centimeters. So the diameter is 5.12 centimeters. Okay, so that was solved this part of the problem, right? Now we want to solve the next part of the problem. If instead the angle must given at buckets an upward acceleration of 0.4 meters per second squared, what should the angular acceleration of the axle be? So for this, right, in the same way that we got the value of omega, right, we can get a value of alpha. So the acceleration is going to be alpha r, right? Because acceleration is dv dt. Okay, so the acceleration is the time derivative of the velocity. The angular acceleration is the time derivative of the angular velocity. So because the radius is constant, we can do this, right? We know this is 0.4 centimeters per second squared. This is 2.56 centimeters, right? Because we have the same diameter that we got from the first part. Therefore, alpha is equal to a over r. So this is 0.16 rad per second squared. Okay, so this was a relatively straightforward example. I hope you can see that. And for this example, what I want to show you is basically that the radius of the object that you're dealing with is how you're going to convert between linear motion of an object rotating about that radius to angular motion, right? So this is the first part of solving these problems. For the second part, I want to talk about how to convert between linear kinetic energy and angular kinetic energy. So for this one, I want to talk about a general flavor of problem, which is the dropped mass and axle. So there are many forms of this problem depending on exactly what you're doing. You can think about this as very close to the Atwood's machine problems you were working with, except now the axle is going to have mass. So a simple example of this is imagine that I have a uniform sphere of mass m. Okay? And tied firmly to this sphere is a weight of mass big M. Okay? And what happens is this mass is tied, let's say, to this point up here. And this mass drops to the floor. Okay? And this causes this wheel to rotate. So this mass is going to have some velocity v, and this wheel is going to have some angular velocity omega. And hopefully you can see that as I make this wheel heavier, this mass will drop more slowly. Why? Because we need more rotational kinetic energy. So there are two things that I want to stress when I'm talking about this problem. The first is this. This is an energy conservation problem, right? So we need to write down the total energy of the system. That involves gravitational potential energy, the rotational kinetic energy of the wheel, and the kinetic energy of the mass. And the second thing I want to stress is that there are restrictions. Right? Because this mass is tied to this wheel, when it drops, the wheel rotates. And this connects the rotational kinetic energy of the wheel and the mass of the falling weight. So what I want you to do with these problems is I want you to first write down the conservation of energy law, and then second, apply the restrictions. And then when you apply the restrictions, what you're going to see is that you can plug in various parts of the problem into each other. I want to point out that this is not very different from when we were dealing with ramp problems, right? You would draw the free body diagram, and then you would apply restrictions in order to find the normal forces. And so I want you to see how solving these problems can also help you understand how to go back and solve other problems that may look like they're unrelated. Moving back to this problem, I want to first write down the total energy of the system, right? So, well, first, we need to ask whether mechanical energy is conserved. So in this problem, let's assume that this string is taut and massless, so no work is being done on the string. So all the work in this problem is done by gravity. Therefore, we can say that yes, total mechanical energy is conserved, and I can write down E total is going to be equal to, right, mgh, where I'll call this some height h, right, plus 1/2 m v squared. Okay, so this is the kinetic energy of this mass plus 1/2 I omega squared. Okay, so now we have the next problem, which is what is this moment of inertia? So what you should do at this point is go over to your table of moments of inertia and remember that or you don't have to remember, you can just look it up. For a uniform disk, the moment of inertia is 1/2 m r squared. Okay, so if this disk is some radius r, then we can calculate this. So then if we plug this value in here, now the total energy becomes mgh plus 1/2 m v squared plus 1/2 m r squared omega squared. Okay, now I want to apply restrictions. And by that I mean I know that this mass m, if it moves by some amount, this wheel must rotate by the same amount. So we can formalize this, right? If this is my delta theta of my wheel, right, then this is delta s. This is the change in the total distance covered by some object on the edge of the wheel, which is equal to my string, which is the same as delta h of the mass. Also, you'll notice that for the angular speed, right, the velocity of the outside of the wheel is omega r. Therefore, we have two restrictions. One is delta h is equal to, right, of course, the velocity of the wheel delta t, which is also equal to omega r delta t. So this is the path coverage in the same time interval. A second way of thinking about this set of restrictions is that omega r is equal to the speed of the mass, right? So if the mass is dropping, the angular speed of the wheel is the same. Therefore, the total energy of the system, plugging in both of these equations, is mgh plus 1/2 m v squared plus 1/2 m, and then we can write this part, right? We can substitute either the velocity for the angular velocity or vice versa. So I'm going to choose to write this as m v over r squared need to put my moment of inertia in there. Okay, so this is the moment of inertia, and this is 1/2 VR squared. So you'll notice these radii cancel, okay? And therefore this becomes mgh plus 1/2 m v squared plus 1/4 m v squared. So effectively, you can think about this as, because I'm also adding kinetic energy to the wheel at the same rate that I have to add kinetic energy to my mass as it falls, you effectively have to add more kinetic energy to the system for the same change in potential energy. And so what you'll see is that the rock drops more slowly as you have a more massive wheel. In other words, as this m increases. Right? And so using this equation, we can solve for the speed of the wheel as a function of the height that we have traversed and the speed of the mass as a function of the height traversed. So I'm going to do that right now. But you can solve for a lot of other quantities in this problem. So if this is constant, then we can say mg delta h, okay, where for our wheel mass system, delta h is here, right? Minus mg delta h is equal to 1/2 m plus 1/4 m, the velocity of the mass squared, or the speed of the mass squared. So what I gave you was two examples of how to understand rotational kinetic energy and angular acceleration and angular velocity in terms that you've seen before, relating these to linear quantities. And these will be common examples that you'll see on the homework and common problems that you'll see on the exam. So what I want you to do is figure out, how can I relate the linear momentum and linear kinetic energy that I've seen before to their angular equivalents, and how do I convert between them? So the dropped flywheel was one example, but we're going to see more examples, and you have an example on your exam review about a dropped yo-yo, which is very similar to this. You're going to see problems involving rolling objects that are very similar to this. And when you do momentum conservation, you're going to see equivalent conversions between linear and angular momentum that are similar to this. So, as always, thank you for watching, and let me know if you have any questions on this.